Hello there. Steve here. Welcome back to another Sleepy Steve story. Before we drift off tonight, remember to subscribe to help Steve-O out, and I will keep making more sleepy stories to help you study gently, revise quietly, and settle your mind at the end of the day. Tonight, we are staying in Unit 3 Chemistry, Area of Study 2. We have already thought about reaction rates. We have already slowed down collision theory. We have already walked carefully through equilibrium and Le Chatelier's principle. Now we are going to bring those ideas together. Tonight is about optimizing industrial chemical processes. That sounds like a very busy phrase, but we can make it calm. Optimizing simply means choosing conditions that make a process work as well as possible. In chemistry, that usually means thinking about how fast a reaction happens, how much product is made, how much energy is used, how much waste is produced, how safe the process is, how expensive it is, and how sustainable it is. You might picture a large chemical plant at night, not loud, not rushed, just a quiet industrial landscape under soft lights. Pipes run neatly along metal frames. Tanks stand still against the dark sky. A control room glows gently through the windows. Inside, scientists and engineers are not guessing. They are using chemical principles. They are asking careful questions. Should the temperature be higher or lower? Should the pressure be increased? Should a catalyst be used? Should the products be removed as they form? Should the reaction be allowed more time? And how can the process be designed so that it is efficient, safe, economical, and responsible? This is the calm center of industrial chemistry, not just making chemicals, but making them wisely. So take a slow breath in and a slow breath out. Let the control room become quiet. Let the lights soften. And let us begin with the idea of optimization. In VCE chemistry, when we talk about optimizing a chemical process, we are usually balancing several goals at once. One goal is rate. A fast reaction can produce more product in a shorter time. That can be useful in industry because time, equipment, and labor all cost money. Another goal is yield. Yield is the amount of desired product produced. A high yield means more of the reactants have been converted into useful product. Another goal is cost. A process may be chemically possible, but too expensive to operate. Another goal is safety. High pressure, high temperature, toxic substances, or flammable materials may increase risk. Another goal is environmental impact. A process that uses large amounts of energy, releases greenhouse gases, produces toxic waste, or wastes raw materials may be less sustainable. So an optimized process is not always the process that gives the highest possible rate, and it is not always the process that gives the highest possible yield. It is usually a compromise, a careful balance, a set of reaction conditions chosen because they are suitable overall. This is an important Unit 3 idea. In exam answers, you often need to explain not just what happens to rate or yield, but why industry may choose conditions that are not perfect in one direction. A very high temperature might make particles move faster and increase the rate, but it might also cost more energy. And if the forward reaction is exothermic, a higher temperature might reduce the equilibrium yield. A very high pressure might increase yield for some gas reactions. but it may require strong equipment, greater energy input, and more safety controls. A catalyst might increase rate without changing equilibrium yield. But the catalyst may be expensive or sensitive to impurities, so optimization is about chemistry and judgment together. Now let us begin with reaction rate. Rate tells us how quickly reactants are converted into products. In collision theory, a reaction only occurs when particles collide with enough energy and the correct orientation. If we want to increase the rate, we need to increase the number of successful collisions per unit time. This can be done in several ways. We can increase temperature. At a higher temperature, particles have more kinetic energy. They move faster, they collide more often, and a greater proportion of particles have energy equal to or greater than the activation energy. This means more successful collisions occur, and the rate increases. In industry, increasing temperature can be useful because it speeds up production. But higher temperature also means higher energy cost. It may also create safety issues. And for reversible reactions, it can shift the equilibrium position depending on whether the forward reaction is exothermic or endothermic. This is where rate and yield begin to pull in different directions. Imagine an exothermic forward reaction. The reaction releases heat. If temperature is increased, Le Chatelier's principle says the equilibrium system will favor the endothermic direction to partly oppose the change. For an exothermic forward reaction, that means the reverse reaction is favored. The equilibrium yield of product may decrease, so higher temperature increases rate but may lower yield. Industry may therefore choose a moderate temperature, not too low because the reaction would be too slow, not too high because the yield may be reduced and energy costs may rise. A moderate temperature is often a compromise between rate, yield, and cost. Now let us think about pressure. Pressure matters most when gases are involved. Increasing pressure pushes gas particles closer together. The particles collide more frequently, so increasing pressure can increase the rate of a gas reaction. Pressure can also affect equilibrium position. If a reversible reaction has fewer moles of gas on one side of the equation, increasing pressure will favor the side with fewer gas particles. The system shifts to reduce pressure. For example, if the product side has fewer moles of gas, increasing pressure can increase the equilibrium yield of product. That sounds useful, but again, industry must compromise. Very high pressure requires strong reaction vessels, compressors, safety systems, and energy input. It can increase production costs and hazards. So the chosen pressure may be high enough to improve rate and yield, but not so high that the process becomes unsafe or uneconomical. Now, let us think about concentration. For reactions in solution, increasing the concentration of reactants usually increases the rate. There are more particles in a given volume. There are more collisions, and therefore there may be more successful collisions each second. For equilibrium systems, changing concentration can also shift the equilibrium position. If reactant concentration is increased, the system will tend to consume some of the added reactant, favoring the forward reaction. If product is removed, the system will tend to replace some of the product, again favoring the forward reaction. This can be used in industrial processes. Removing product as it forms can help drive the reaction forward. Adding an excess of one reactant can also shift equilibrium toward products. But using excess reactant can increase cost, create waste, or require recycling. So again, the industrial chemist asks, is the benefit worth the cost? Now, let us think about catalysts. A catalyst increases the rate of a reaction by providing an alternative reaction pathway with a lower activation energy. Because the activation energy is lower, a greater proportion of particles can react successfully at a given temperature. This means the reaction can happen faster. A catalyst is not consumed in the overall reaction. It does not change the enthalpy change. It does not change the equilibrium constant, and it does not change the final position of equilibrium. This is a very important exam point. A catalyst increases the rate at which equilibrium is reached, but it does not increase the equilibrium yield. In industry, catalysts are extremely valuable. They can allow a process to run at a lower temperature. This can reduce energy costs. They can increase the rate of production. They can improve selectivity, meaning more of the desired product and fewer unwanted byproducts may form. They can reduce waste. They can support greener chemistry. But catalysts can also have limitations. They may be expensive. They may be poisoned by impurities. They may require specific conditions. They may need to be replaced or regenerated. So an exam answer about catalysts should be precise. A catalyst lowers activation energy and increases rate. It does not change Kc. It does not shift equilibrium. It does not increase the percentage yield at equilibrium. But it can make the process more efficient, because the desired amount of product can be formed in a shorter time or at a lower temperature. Now let us walk quietly through a classic industrial example, the Haber process. The Haber process produces ammonia from nitrogen and hydrogen. Nitrogen gas reacts with hydrogen gas to form ammonia gas. The reaction is reversible. It is exothermic in the forward direction, and there are fewer moles of gas on the product side. This makes the Haber process a useful example of optimization. First, temperature. Because the forward reaction is exothermic, a lower temperature would favor the production of ammonia at equilibrium. Lower temperature would give a higher yield, but at low temperature, the reaction rate would be slow. The particles would have less kinetic energy. Fewer particles would have energy greater than or equal to the activation energy. So ammonia would form too slowly for efficient industrial production. A higher temperature would increase rate, but it would favor the reverse, endothermic direction, reducing the equilibrium yield of ammonia. So industry uses a compromise temperature, warm enough for a reasonable rate, not so hot that the yield becomes too low. Second, pressure. There are 4 moles of gas on the reactant side, 1 mole of nitrogen plus 3 moles of hydrogen. There are 2 moles of gas on the product side, 2 moles of ammonia. Increasing pressure favors the side with fewer moles of gas, so higher pressure favors ammonia production. It can also increase reaction rate because gas particles are closer together and collide more frequently. But very high pressure is expensive and potentially dangerous. So industry uses a compromise pressure, high enough to improve yield and rate, not so high that the cost and safety risks become unreasonable. Third, catalyst. The Haber process uses an iron catalyst. The catalyst increases the reaction rate by lowering activation energy. It allows the process to operate efficiently without requiring an extremely high temperature. But the catalyst does not change the equilibrium yield. It simply helps the system reach equilibrium faster. Fourth, product removal and recycling. Ammonia can be removed from the reaction mixture as it forms. This reduces the concentration of product. According to Le Chatelier's principle, the system responds by favoring the forward reaction to replace some of the removed ammonia. Unreacted nitrogen and hydrogen can be recycled back through the reactor. This improves overall efficiency and reduces waste. So the Haber process is not optimized by one simple choice. It is optimized through a system of choices: temperature, pressure, catalyst, product removal, recycling, safety, cost, energy use, and yield. That is exactly the kind of thinking VCE chemistry often rewards. Now let us move from this example to broader industrial process design. A chemical process may involve many stages. Raw materials must be obtained. Reactants may need to be purified. The reaction must be controlled. Products may need to be separated. Byproducts may need to be treated. Unreacted materials may be recycled. Energy may need to be supplied or recovered. Waste may need to be reduced. Safety systems must be maintained. So when chemists evaluate a process, they often look beyond the balanced chemical equation. The equation is important. It tells us the mole ratio. It tells us reactants and products. It may tell us whether the reaction is reversible. But the industrial process also asks practical questions. Are the reactants available? Are they renewable or non-renewable? Are they hazardous? How much energy is required? What is the percentage yield? What is the atom economy? Are there toxic byproducts? Can waste be recycled? Can the process be made safer? Can the product be produced at a cost that is realistic? In Unit 3, this is where chemical knowledge connects with sustainability. A process may be efficient in terms of yield, but poor in terms of environmental impact. Another process may have a slightly lower yield but use less energy, produce less waste, or rely on safer conditions. So a modern chemical process is evaluated by more than one measure. Let us pause on two useful measures: yield and atom economy. Percentage yield compares the actual yield to the theoretical yield. The theoretical yield is the maximum amount of product that could be produced according to the stoichiometry of the reaction. The actual yield is the amount of product actually obtained. Percentage yield is calculated by dividing actual yield by theoretical yield and multiplying by 100. A high percentage yield means the process has successfully converted a large proportion of the expected product. But percentage yield does not tell the whole story. A reaction could have a high percentage yield and still produce a large amount of unwanted byproduct. This is why atom economy is also useful. Atom economy considers how many atoms from the reactants end up in the desired product. A process with high atom economy uses raw materials efficiently. A process with low atom economy may produce more waste, even if the main product is obtained in good yield. For green chemistry, high atom economy is desirable because it reduces waste and improves resource efficiency. Now let us think about energy. Industrial chemical processes often use large amounts of energy. Heating reactors, compressing gases, cooling products, separating mixtures, and purifying substances all require energy. If the energy comes from fossil fuels, the process may contribute to greenhouse gas emissions, so process optimization includes energy efficiency. A catalyst may allow lower operating temperatures. Heat released from an exothermic reaction may be captured and reused. Insulation may reduce heat loss. Continuous processes may be designed to use energy more efficiently than batch processes in some contexts. Renewable energy sources may be used where possible. Again, the chemistry is connected to design. Now, let us think about waste. Waste can include unwanted byproducts, excess reactants, solvents, contaminated water, gases released to the atmosphere, or solid residues. Reducing waste can improve sustainability and reduce cost. Unreacted reactants can sometimes be recycled. Solvents can sometimes be recovered and reused. Byproducts can sometimes become useful feedstocks for another process. Reaction pathways can sometimes be redesigned to produce fewer waste products. This links to the principles of green chemistry. Green chemistry aims to design chemical products and processes that reduce or eliminate the use and generation of hazardous substances. For VCE chemistry, you do not need to turn the story into an environmental slogan. You need to explain the chemistry behind the evaluation. If a process uses a catalyst, it may reduce energy use because it allows the reaction to proceed at a lower temperature. If a process recycles unreacted reactants, it can reduce waste and improve overall conversion. If a process has a high atom economy, more of the reactant atoms become useful product. If a process uses safer solvents or milder conditions, it may reduce risk. This is the kind of linking language that makes an answer stronger. Now let us imagine the control room again. A small graph shows reaction rate, another screen shows temperature, another shows pressure, another shows the concentration of reactants and products. In a real process, these conditions are monitored carefully. If the temperature is too low, the rate may fall. If the temperature is too high, the equilibrium yield may fall for an exothermic reaction, or safety limits may be exceeded. If pressure is too low, gas collisions may be less frequent, and equilibrium may not favor the desired product. If pressure is too high, the equipment may be under excessive stress. If impurities enter the system, a catalyst may become poisoned, and the rate may decrease. If product is not removed efficiently, the equilibrium position may not be driven forward as effectively. So optimization is not a single moment. It is ongoing control. A process is designed, monitored, adjusted, and evaluated. For exam purposes, it is helpful to use a simple pattern. First, identify the reaction feature. Is it reversible? Is it exothermic or endothermic? Are gases involved? Are there more moles of gas on one side? Is a catalyst present? Second, identify the change in conditions. Temperature, pressure, concentration, catalyst, product removal. Third, explain the effect on rate. Does the change affect collision frequency? Does it affect kinetic energy? Does it affect activation energy? Fourth, explain the effect on equilibrium yield. Does the system shift forward or reverse? Does Kc change? Does equilibrium yield increase, decrease, or stay the same? Fifth, evaluate the industrial compromise: cost, safety, energy, sustainability, waste, overall efficiency. Let us practice that gently with temperature. If temperature increases, particles have greater kinetic energy. This increases the frequency of successful collisions and increases the rate. For an exothermic forward reaction, increasing temperature favors the reverse endothermic direction, so the equilibrium yield of product decreases. Therefore, industry may choose a moderate temperature to balance a reasonable rate with an acceptable yield and manageable energy cost. That is a strong answer because it links rate, equilibrium, and industrial compromise. Now, pressure. If pressure increases for a gas reaction, particles are closer together and collide more frequently, increasing the rate. If the product side has fewer moles of gas, increasing pressure favors the product side, increasing equilibrium yield. However, very high pressure requires stronger equipment, increases cost, and increases safety risk. Therefore, a compromise pressure may be chosen. Now, catalyst. A catalyst provides an alternative pathway with a lower activation energy. This increases the rate and allows equilibrium to be reached more quickly. The catalyst does not change Kc and does not change the equilibrium yield. However, it can improve industrial efficiency by increasing production rate and allowing lower operating temperatures, which may reduce energy costs. Now, product removal. If product is removed from a reversible system, the concentration of product decreases. The system responds by favoring the forward reaction to replace some of the product. This can increase the amount of product formed overall. However, separation and removal may require energy, equipment, and cost. Again, the process must be evaluated. Now, let us settle into the idea that industrial chemistry is full of compromises. Chemistry students sometimes want one perfect answer: the highest temperature, the highest pressure, the strongest concentration, the fastest reaction. But industry rarely works that way. A reaction that is very fast but unsafe is not optimized. A reaction with high yield but huge energy cost may not be optimized. A reaction that produces product cheaply but creates toxic waste may not be optimized. A reaction that works in theory but uses rare or expensive catalysts may not be optimized. The best process is the one that balances the important conditions for that particular reaction and purpose. That is why process design uses chemistry, engineering, economics, and environmental thinking together. Now, as the lights in the control room grow softer, let us gather the episode into a simple memory. Rate is about how quickly product forms. Yield is about how much desired product forms. Equilibrium position is about the relative amounts of reactants and products at equilibrium. Temperature can affect both rate and equilibrium. Pressure can affect gas reactions and equilibrium systems with different numbers of gas particles. Concentration can affect rate and can shift equilibrium. A catalyst increases rate but does not change equilibrium yield. Removing product can drive a reversible reaction forward. Recycling unreacted reactants can improve resource use. High atom economy reduces waste. High percentage yield improves production efficiency. Lower energy use, safer conditions, and reduced waste support sustainability. And industrial optimization is the careful balancing of these ideas. So when you see a question about optimizing a chemical process, do not panic. Read the equation slowly. Look for gases. Look for enthalpy information. Look for reversible arrows. Look for conditions. Then explain the effect on rate, explain the effect on yield, and finish with the compromise. That is the calm shape of the answer. The chemical plant is quiet now. The reactors are steady. The pipes are warm. The control room lights are low. Somewhere particles are colliding. Some are reacting. Some are reaching equilibrium. And the process, carefully designed, keeps moving toward useful product with less waste, less energy, and more thoughtful chemistry. This has been Sleepy Steve. Sleep well and let the idea settle gently in your mind. Optimization is not one perfect setting. It is the careful chemical balance between rate, yield, cost, safety, and sustainability.